This is the first in several tutorials on equilibrium and working through some problems. And equilibrium is exactly what it sounds like. The forces equal each other or cancel each other out. So all the forces that are up balance out the forces that are down. The forces that are left balance out the forces that are right. And the law of motion that discusses when forces are balanced is the first law of motion. It says either an object stays at rest or an object stays moving at a constant velocity. So if you see either that the object is at rest or moving at a constant velocity, you know we're in equilibrium, and therefore there's no acceleration. So what does that mean if there's no acceleration? Well, first of all, to solve these problems, we want to draw our free body diagram. We discussed earlier what goes into a free body diagram. First, gravitational force is almost always present. We're almost always on the Earth, and that is always directed down. If there is a surface, then we can have a normal force perpendicular to the surface, and either static or kinetic friction, which is parallel to the surface and opposite the direction being moved. It is static if the object is not moving, and is kinetic if the object is sliding on the surface. If there is a string, rope, or cable, anything like that, there is tension that is present, and any other forces that would be given to you would be considered applied forces. We of course then write down our givens, what we need to find, and finally we write down our equations. Now if you are in equilibrium, the answer is yes to that question, are you in equilibrium? Then we have that the total forces left and right are equal to 0, so the sum of the forces in the x direction are 0, sigma f. And if the total force up and down would also be 0, then sigma fy would also be 0. If the answer is no, and we'll do those problems later, but if the answer is no, then the total force, sigma f, is equal to mass times acceleration. So the first problem we want to go through is really in two parts. We have a museum curator that wants to move a 145 kilogram aluminum sculpture across a horizontal steel platform. It takes a force greater than 870 newtons to move the sculpture. What is the coefficient of static friction between the aluminum and the steel? So first we draw our free body diagram, and we have, of course, first force is gravitational force. We write that in. Then we have a normal force. We have a surface, so there's a normal force perpendicular to that surface, in this case up, supporting that statue. If we were to push the statue to the right, then the friction would be to the left, opposite the direction we are pushing it. It says it takes a force greater than 870, so at this point, at 870 newtons, it is not moving. That makes it static friction. We are applying a force to the right at 870, that is our applied force. So we have a free body diagram, and then we write down our givens. We know that it is a 145 kilogram statue, and that is considered the mass because it is in kilograms. And then we also know that it's an 870 newton force. That is how much force we are applying to the statue. So we're just doing letter A right now. We want to find the coefficient of static friction. Well, there is only one equation with the coefficient of static friction, and that equation is, if we go to our equation sheet right here, but we don't know either the static friction nor do we know the normal force. So we're kind of stuck right now, but let's write down the equation because we will have to use that. I'll put a box around what we're trying to find. We'll leave that for later. For now, what we have to do is we have to go to our conditions of equilibrium. We know that it is not moving, it's staying at rest. And so therefore, what we want to do is write down that the total force in the x is 0 and the total force in the y is 0. But before we proceed with that, what I might recommend is whenever you're given the mass and not the gravitational force, always solve for that gravitational force by multiplying by the gravitational field constant. So whenever you're given the mass, take that mass and multiply by your 9.81 newtons for every kilogram. Make sure you're in kilograms though. We get the gravitational force in this case to be 1,422.45 newtons. So we really know two of the four forces. Unfortunately, the two we don't know are the two we need for our equation. So I'm going to go to a different flip chart here, and we'll write down our two conditions of equilibrium. First, the total force in the x is 0. And the second condition of equilibrium is the total force in the y is equal to 0. So going back to our free body diagram, in the x direction, there's two forces, static friction and applied force. The total of those equals 0. However, at this point, I want to put in any positives or negatives. Static friction is to the left, so that is negative. We can put in the applied force. We know that one. It's 870 newtons. And so we can solve for a static friction. It is also 870 newtons. Looking in the y direction, we see that we have two forces in the y direction, normal and gravitational force. So the sum of those is 0. But again, we want to look at positive and negatives. Normal force is up, so that is positive. Gravitational force is down, so that is negative. And we solve for that gravitational force. It is 1422.45 newtons. So therefore, our normal force is also 1,422.45 newtons. So now we know those two forces, and we can come back here and solve for our unknown. We now know these two forces. Static friction is 870, and the normal force is 1,422.45. Now when we write it into this equation, we are using just the magnitude, absolute value for this equation. So never put positive negatives into that equation, just absolute value. We get our coefficient of static friction, comes out to be 0.61. We'll need another tutorial here on finding the coefficient of kinetic, and we should find something less.